Okay, let's have a look at at the circuit that I will draw on a picture. This circuit will contain inductor. This is inductor. It will contain inductor and a few other elements. And a few other elements. The next element is resistance, inductor resistance. This is resistance, and the source of electromotive force, source of energy. Source of energy, it is here. Here, this is a source of energy. So let's connect these elements. So inductance, resistance, electromotive force, internal electromotive force, and let's connect these elements. Let's connect these elements. Let's connect these elements. Here we have this wire and here we have switch. We have key that let us switch the direction of electric current. With this key, we may switch direction or change direction of electric current. With this key. This key, it may be assigned with key. Okay, and have a look at this circuit. At initial moment in time, the switch is turned in vertical direction. So at initial moment in time, we have direct current. In this direction at initial moment in time, and then we change direction of this key into horizontal direction. Then we switch current to horizontal direction. What will happen? This source of electromotive force will be disconnected. It will be removed from this circuit, and the electric current will be in this spot. And it will not be direct current. because there are no source of energy anymore. So this electric current will decrease. This electric current will decrease, and energy will decrease. Energy will decrease, and uh, this energy will be lost in resistance. So resistance will be heated. And energy will decrease. And let's try to calculate this energy. Let's try to calculate this energy. From one of our previous lessons, we know that electromotive force, electromotive force of self-induction is in this element, in this induction coil. Electromotive force of self-induction, ES, it is equal to work, or it is better to write this in differential form. So differential of work divided by differential of electric charge. And from other side, we know from our previous lecture that electromotive force of self-induction, according to Faraday's law, is equal to minus L and first derivative of electric current is time, equal to first derivative of electric current by time. Okay, and let's substitute this into this. So from these two equations, we will obtain that this derivative is equal to this expression. And from here we can make a conclusion that dA is equal to minus L dq dt and di. But we know that the first derivative of electric charge is equal to electric current according to the definition of electric current. So we can remember that electric current is equal to the derivative of this, derivative. So we may substitute this here, and we will obtain that differential of work is equal to minus L I and d I. Okay, and we have explicit functions. We have explicit functions in left side and the right in the right side of equations. It means that we may integrate this differential equation. This differential equation. So from here we have that A work is equal to definite integral from 0 to full work, and this is equal to definite integral minus L I and D I, and here will be uh, what limits will be here. It will be from some initial current I to zero. Why? Because current decreases. Current decreases from I to zero because of leak of energy on resistance. Because of leak of energy on resistance. And so from here we can calculate this integral. We can calculate this integral. It will be minus L integral from I to 0, and I and D I, and it will be equal to L integral from 0 to I, and here we will have I have changed the places of integral limits, and I have changed a sign in front of this integral, sign near this integral. So this is easy to calculate. It will be equal to L I to the power of 2 divided by 2. Okay, do you have any questions about this? No questions. And how this work was done? We know that according to the according to the law of conservation of energy, we need energy to do the work. We need energy, and how did this energy appear, and where have this energy appeared? Where have this energy has this energy appeared? This energy appeared from magnetic field inside the inductor. So according to this expression, and according to the law of conservation of energy, we may conclude that energy of magnetic field inside some element with inductance is equal to L electric current to the power of 2, and divided by 2. And this formula may also be written in some other form, and and according to if you remember that flux linkage is equal to inductance multiplied by electric current, we may use this formula. We may use this formula to uh, write here another form of this equation. So we can make substitution, and we will get I C divided by 2. Or we can also write another one form of this equation: flux linkage to the power of 2 divided by 2 L. Okay, what questions do you have about this? No questions. No questions. Okay, if there are no questions, let's write this formula in frame. This is energy of magnetic field. Energy of magnetic field. Magnetic field in element with inductance. For example, in solenoid. So this formula is appropriate. This formula is appropriate for any element with inductance, and for example, in solenoid. Uh, so, do you have any questions about this? Uh, okay. Let's try to use this formula for solenoid. From our previous lesson, we can remember that inductance of solenoid is equal to uh, magnetic permeability multiplied by magnetic constant, and n to the power of 2. N is the number of turns per unit of length. And we know that and multiplied by volume inside solenoid. It is for simple straight solenoid. Inductance may be calculated with such formula. And we know that magnetic field inside solenoid may be calculated by formula mu 0 n multiplied by electric current. And it means that electric current in solenoid is equal to magnetic inductance divided by mu magnetic permeability, magnetic constant, and number of turns per unit of length. Okay, so from here we have that energy of magnetic field in solenoid is equal to L to the Li to the power of 2 divided by 2, and we may substitute these two formula here. May substitute these two formula in here. So we will obtain that it will be multiplied by b to the power of 2 divided by 2 mu to the power of 2 mu 0 to the power of 2 and n to the power of 2 n to the power of 2. So we have obtained that this energy is equal to b to the power of 2 divided by 2 mu 0 v volume inside the solenoid. Okay, what questions do you have about this? What questions do you have about this? No questions. No questions. Okay, there are no questions. I will clean some things that we don't need anymore in this situation. And and from here we can say that we can obtain from here energy density of magnetic field. So it will be omega m. Omega m is equal to W divided by V. This is true because magnetic field inside an ideal solenoid is homogeneous. Magnetic field inside ideal solenoid is homogeneous, and this means that it will be b to the power of 2 divided by 2 mu 0, and it can also be written in some other forms. If we remember that magnetic induction B is equal to mu 0 magnetic field intensity H. So we can write that it will be equal for isotropic magnetics. It will be B H divided by 2. And it can also be written as mu 0 h to the power of 2 divided by 2. Divided by 2. Okay, what questions do you have? What questions do you have? No questions. No questions. Okay, if there are no questions, we may write this formula. We may write this formula in next way. So this is energy density of magnetic field. Energy density of magnetic field. If we remember one of our previous lectures, we may remember that energy density of electric field may be calculated with a very similar formula. That is electric field induction to epsilon 0 is equal to d e divided by 2, and this is equal to epsilon 0 e to the power of 2 divided by 2. So so this is energy density of electric field. Energy density of electric field, and this is energy density of magnetic field. 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 So according to the written formula, the energy of electromagnetic field, in some volume, energy of electromagnetic field may be calculated with formula W is equal to triple integral W omega dV. Omega dV. And what is omega? Omega is just sum of energy densities of electric and magnetic field. So omega is equal omega E plus omega M. Is equals omega M. It is just energy density of electromagnetic field. Energy density of electromagnetic field. Energy density of electromagnetic field. Electromagnetic field. Of electromagnetic field. And I will write this formula in frame. And we have shown that electromagnetic field has its own energy, and this energy may be calculated with this formula, that are written on the screen. Okay, what questions do you have? No questions. No questions. Okay, let's generalize our knowledge, all our knowledge about electromagnetic field. Let's generalize all our knowledge about electromagnetic field. First of all, we know Maxwell-Faraday equation. We know Maxwell-Faraday equation from one of our previous lessons. According to this equation that we studied a few lessons before, according to Maxwell-Faraday's equation, linear integral E dl is equal to minus surface integral SL surface integral SL dB dt ds dB dt and ds. And the next equation is Ampere's circuital law. Ampere's circuital law. Ampere's circuital law is it means that integral of h dl is equal to the sorry, it is not integral on closed surface, so we don't need round here. So it is equal to surface integral SL surface integral SL. Here we have electric current density plus so-called Maxwell's addition. This result comes from experiment. That change in electric field will produce magnetic field, and these experiments have shown that it is necessary to make this addition that is known as Maxwell's addition. So this is Maxwell's addition. So this is Ampere's circuital law. With Maxwell's addition. Okay, and the next equations that we studied before was Gauss theorem or Gauss-Flux law. Surface integral surface integral along closed surface d and ds. We have learned this, and this is equal to this is equal to triple integral vs rho q, density of electric charge, or electric charge density, and dv. And dv. Sorry, we have some problems. Sorry for disconnect. We have problems with energy in Ukraine, but I will continue. I will continue with my additional battery. So let's try to remember. What we have done. Before. Yes, it is here. It is here. So this is Gauss flux law. This is Gauss flux law. So here we have differential dv, and the last fundamental equation is Gauss flux law for magnetism. According to this law, we have surface integral of magnetic induction ds, and this is equal to 0. This equation shows absence of magnetic charges, and these four equations together are known as Maxwell's equations, or Maxwell-Heaviside equations, Heaviside equations. So they are Maxwell's equations. Maxwell equations or Maxwell-Heaviside equations. Maxwell-Heaviside equations in integral form. And this is necessary. To add some relations to these equations, and according to these relations, the vector D, vector of electric induction, vector of electric induction or electric displacement vector is equal to epsilon 0 E, and this also equal to, and we may write a very similar equation for magnetic field. Magnetic induction is equal to mu 0 H. Very similar for magnetic field. Very similar for magnetic field, and Ohm's law. Ohm's law in differential form. Electric current density is equal to electric conductivity multiplied by electric field intensity. Okay, what questions do you have about this? What questions do you have about this? No questions. No questions. Okay, if there are no questions, I will write this in frame. And of course, if we have integral form, we should always have differential form of these equations. So I can rewrite these equations in differential form. And in this situation, what will we have? Instead of integral in this right side, I will have Carl operator. So here will be Carl E, and this will be equal to minus B dt. This will be equal to derivative of simple derivative of magnetic induction, partial derivative of magnetic induction. Okay, what about Ampere's circuital law? The situation is almost the same. Instead of linear integral, we have Carl operator. And we should remove surface integral in right side of equation. We should remove surface integral. So this is Ampere's circuital law. Okay, what about this? Surface integral in left side should be replaced with divergence operator. This should be replaced with divergence operator. It should be replaced with divergence operator. and the triple integral just should be replaced, should be removed from here. And this is differential form of Gauss flux law. And what about this? What about this? Let's replace surface integral with divergence operator. With divergence operator. With divergence operator. With divergence operator. And this formula will be without any changes. Without any changes, because they don't contain any integrals or derivatives. So this is Maxwell's equations in differential form. Maxwell's equations in differential form. Okay, that's all about electricity and magnetism. That's all about electricity and magnetism. So, do you have any questions? Do you have any questions about this? No questions. No questions. Okay, there are no questions. So let's start. Let's start a new. Let's start some new some new topic. A new topic that is connected. That is related to mechanical oscillations. It's related to mechanical oscillations. So I will clean my screen because we don't need anymore this formula from electricity and magnetism. And let's try. Let's start with simple free mechanical oscillations. With free mechanical oscillations, and let's have a look at simple harmonic oscillator. What is this? What is simple harmonic oscillator? Without any friction, damping, or something like this. So simple harmonic oscillator. Simple harmonic oscillator. What is this? This is just spring connected to the wall. Wall is fixed, and here we have some mass. Here we have some mass. Here we have some mass m, and spring has spring constant. Spring has a spring constant. Spring constant. For example, key. Spring has spring constant. Spring constant key. Spring constant key. Okay, and let's draw an axis x. Axis x. What do we know about this system? We know that according to Hooke's law, we have only one force in this system. Only one force in this system. We know that This force is directed opposed to spring deformation. So the force, uh, elastic force is equal to k multiplied by x. Minus k multiplied by x. Minus k multiplied by x. Okay, and what about what can we do with how to calculate dynamics of this system? We may use Newton's second laws of motion. Newton's second law of motion. According to this law, mass multiplied by second derivative is equal to F. And this is equal to F. Okay, and let's substitute this force. Let's substitute this force here, and we will obtain that it is equal minus k x and from here we can write that we can obtain differential equations d2x by dt to the power of 2 dt and plus k divided by m x, and this is equal to 0. This is equal to 0. And this equation is often written in next form, in next canonic form, that according to this this equation is often written in this way: the power of 2x omega 0 and what is omega 0 in this situation? What is omega 0? Omega 0 is so called natural frequency. In this, according to, if we compare these two equations, we may know that natural frequency is equal to square root of k divided by m. K divided by m. This is natural frequency. And as it will be shown in future, that this natural frequency is always connected with the period of oscillation. So period of oscillations is equal to p. This is always connected with natural frequency, and it will be 2p square root of m divided by k. Okay, so this is natural frequency. Natural frequency. Natural frequency, and this is period of free oscillations. Period of free oscillations. Period of free oscillations. Okay, what questions do you have? No, no questions. Okay, so we have differential equations of free oscillations. We have differential equation, and we have formula for natural frequency, and for period of free oscillations. Period of free oscillations. In this case, in case of simple harmonic oscillator. So this is simple harmonic oscillator. Simple harmonic oscillator. A simple harmonic oscillator. A simple harmonic oscillator. Okay, let's have a look. Let's have a look at some another example. Let's have a look at some another example. Another example will be torsional pendulum or torsional pendulum. What is this? Torsional pendulum. Torsional pendulum. Torsional pendulum. In this system, we have some, for example, we have some disk. We have some disk. We have disk with moment of inertia. With moment of inertia I. So we have disk. We have disk, and this disk is connected. This disk is connected to a wire or string, wire or string, and it may be in torsional oscillations. So it may rotate. It may rotate in this direction. It may rotate in this direction. Okay, and what can we do in this situation? According to the law of rotation, or according to the law of rotation dynamics, for rotation dynamics, we can write that moment of inertia multiplied by derivative of angular velocity by time, and this is equal to moment of force. Okay, and if we remember that angular velocity is derivative of angle of rotation. So angular velocity is always equal to first derivative of angle by time. And what about moment of force, or what about torque? M is torque or moment of force. Torque or moment of force. In this case, it will be just another form of Hooke's law. It will be some minus d multiplied by phi, where phi is angle of rotation, and d is some coefficient. D is some coefficient. Okay, and let's make substitutions. Let's make substitutions, and we will obtain I second derivative dt to the power of 2, and it will be minus d phi. Will be minus d phi. Minus d phi. Okay, and we may transform this equation. We may transform this equation, and we'll get that d divided by I phi, and this is equal to 0. This is equal to 0, and this equation may be written in another form. So it will be just here omega 0 to the power of 2. Omega 0 to the power of 2. Where omega 0 is natural frequency. This is natural frequency. So we have very similar situation as it was before. So we have that natural frequency is equal to square root of coefficient of d. Coefficient d. D is known as a torsional constant. This value is known as a torsional constant. So this is natural frequency. Is natural frequency. Natural frequency. And what about period of free oscillations? Will be also very similar. It will be 2 P. So T0 is equal to 2P divided by omega 0, and this will be 2P square root of I divided by D. So this is period of free oscillations. Period of free oscillation. This is a period of free oscillation. Okay, what questions do you have? No questions. No questions. No questions. Okay, if there are no questions, I will clean the screen. I'll clean the screen. Maybe it is necessary to. Maybe it is necessary to change this frame in blue. It will be more. It will be more correct for these situations. For this situation, and okay, D is torsional constant. Maybe I will write this. D is torsional constant. Because I is moment of inertia, we already know this value, and this is torsional constant. Torsional constant. Torsional constant. And this is torsional constant. Okay, what questions do you have? No questions. No questions. Okay, so let's have a look at some another example. Another example. Another example is another example with physical pendulum. Physical pendulum. Physical pendulum. First of all, I will try to draw this. I will try to make a sketch draw. I will try to make a sketch draw for this physical pendulum. Physical pendulum. What is this? Physical pendulum. Physical pendulum. So in this case, we have some massive body with some moment of inertia. We have some massive body. And for example, here we have radius vector. Here we have radius vector. That is equal to r. for example. Radius vector is a radius vector of the center of mass of this physical pendulum, and here we have force of gravity mg, and the angle of rotation is phi. Okay, and the what about axis z? I will write axis z will be perpendicular to the screen and is directed from the screen to us. So this is the axis z. Okay, and what can we do in this situation? In this situation, we will have something very similar to previous case. So the equation of rotation dynamics will be I multiplied by d omega, where omega is angular velocity, or maybe let's write this in this way: second derivative of time, and this is equal to m, where m is moment of force. This moment of force is directed against opposed to angle of rotation phi. So according to the right hand rule, it is directed from us to the screen. And this moment of force m is a result of gravity force. And this is directed from us to the screen. Okay, so how to define this moment of force? First of all, we need to know this distance. This distance from axis to the force. And this is equal to r multiplied by sinus phi. So according to this, we have that m is equal to minus m g r sinus phi. mgr sinus phi. Okay, and what about equation of dynamics? So let's substitute this here, and we will obtain that this is equal to this. This is equal to this. And from here we will obtain that this second derivative to phi and dt second derivative, and this will be not equal. Let's make it in this form: mgr divided by moment of inertia I sinus phi, and this is equal to 0. This is equal to 0. Okay, do you have any questions about this? No questions. No questions. No questions. No questions. And what about this differential equation? It is not non-linear. It is non-linear, but it may be solved. It may be solved analytically, but the solution requires using elliptic integrals. But I think we don't need to use them, because we will deal only with simple case when oscillations are small. So oscillations are small, and this means that oscillations are small. It means that phi is small. Phi is a small value. Is a small value. Phi is a small value. So we will have deal only with a simple case of small oscillations, and if phi is a small value, sinus phi, as you know from calculus, sinus phi is almost equal to phi. And for small oscillations, we will get the equation. When we'll get the equation when we'll get the linear equation. We'll get linear equation. So for this case, we will have that we will have very similar formula. So we'll have very similar formula, and but how to write this in a proper way. So it will be mg mgr divided by I square root and here we will have a square root of m. Of I divided by m g r. Square root divided by m g r. So this is a period of free oscillations. For physical pendulum. Of course, it derives from this equation. It derives from this equation. For physical pendulum, we have very similar situation than it was before. Omega 0 to the power of 2. A very similar situation. Okay, do you have any questions? No questions. Okay, if there are no questions, let's remove some things. And if v is a small value, so we will obtain this equation. We will obtain this equation for physical pendulum that is very similar to previous case. And we may calculate natural frequency and the period of free oscillations for this case. Okay, what questions do you have? No questions. And the last example for today is simple pendulum or mathematical pendulum. Simple pendulum or mathematical pendulum. Simple pendulum or mathematical pendulum. What is this? This system is very similar to system than was before. But so here we have this is here we have some mass on thread, with the length L. So here we have mg, and here will be Here will be length L, and angle of rotation phi. Angle of rotation phi, very similar and very similar axis Z is from screen to us, and the moment of force is from us to the screen. Moment of force is from us to the screen. Okay, and the other things will be very similar to things that was before. Will be very similar to things than it was before. So in this situation, we have very similar situation, but R is equal to L in this situation, and the moment of inertia, this is material point, so moment of inertia is equal to M L to the power of 2, ml to the power of 2. And so it means that we will have in this situation we will have that natural frequency will be square root of G divided by L after substitution, and here will be 2p square root of L divided by G. L divided by G. Okay, natural frequency and the period of free oscillations. The situation is very similar to physical pendulum, but we know that here we have this formula. Okay, and what is the main conclusion of all this situation? We have learned four examples, and for all of them, we have got very similar differential equation, and this equation is known as differential equation of free oscillations. And this equation has the same form for different systems with free oscillations. Has the same form, as you can see here. So the solution will be common for all these situations. Okay, do you have any questions? No questions. Okay, if there are no questions, so thank you for your attention. And I hope to meet you next week.